Happy to be here, and thank you everybody for coming. Also like to thank the organizers for inviting me. I'm one of the old timers, and I think I have a slot for a NASA partner that's used Keck for a long time. Protostars are pretty interesting. I think it's good to know where we come from, where stars and planets come from. But it hasn't been a really popular topic at a lot of these Keck Science meetings, so I thought I'd give a little introductory material. I really love this image here. This is a Spitzer image. Can you hear me okay, or should I take the microphone? Use the mic. Okay. All right. If there's a question, I will use the mic. So, it's a Spitzer image. So blue is 4.5 microns, right? That's really short wavelengths for protostars. So that's like M-band on Keck. And the red is 24 microns, and that's where all these protostars are. There's a cluster of protostars in serpents. So they're pretty embedded. Now, where do we all come from, and what am I going to talk about here? So, star formation. The standard model hasn't changed a whole lot in the last 2 or 3 decades, maybe a little bit. So there are clouds of gas and dust. They get compressed through galactic rotation, environment, and whatnot. There are higher density cores in these dark clouds that will eventually collapse, and a central object forms. And once you have a central hydrostatic object, it is pretty much defined as a protostar. And rapidly, so there's disks forms pretty much at the same time because of conservation of angular momentum as we prefer direction. So matter has to stream onto it from the disk for the most part. And it looks like since the very earliest times, there's also outflow. And that could also maybe help remove angular momentum. But it's inextricably linked. Our accretion onto the disk, through the disk, and outflow. And these disks, I'll show you a little bit what we know about them in the first stage, but they pretty much feed the central object. It takes about 100,000 years to accrete the majority of the mass. And then there's a remnant envelope. You have like a T-Tauri star with a protoplanetary disk after the envelope disperses and helped by these jets driving out the envelope. And eventually you get a weak T-Tauri star with a transition disk, planets, etc. And Bob's your uncle, here we are today. Okay, and then this is a similar schematic drawing, but it shows the observational spectral energy distributions associated with each phase. So this is like this very early phase where the majority of the mass of this early phase called class 0, it's defined by most of the mass to accrete onto the central object. So the central star is just starting to get built up. And these really look very cold. So it was first discovered, this class, in 1993, submillimeter, putting together submillimeter and far infrared data, so almost like a 30 or 40 degree Kelvin black body, at least was the model at the time. And then this next phase is the star is pretty much formed, but there's still a remnant envelope, and this is just kind of like right at the end of the major accretion phase. The disk is still quite massive and active, and then the envelope goes away, and you have this T-Tauri star. So getting back to this one, so there's still a big infrared excess from the envelope. That a lot of that is re-radiation and also emission from the disk. Here, this is just dominated by the disk emission, so this is this excess over the star, over the stellar black body, and then the thin disk is not going to have much radiation after it dissipates. This shows another cut of the observations of these and the evolution. So the ones that are this true protostellar phase that are going through, have recently done a lot of accretion, are these red dots here. The model is that they start off very cold. It's basically just the core is just starting to collapse. There's not much internal heat, not very luminous. And as it collapses, accretion happens at a pretty high accretion rate. And luminosity goes up, and then it flattens out once the accretion flattens out. This is the model. See, a lot of these points are below there. That looks like they're not bright enough to be on this model, so it's interpreted as they are not accreting material in a steady state enough. But this can be solved by having short bursts of accretion, which have been observed in some of these objects. Still a little bit, the jury's still a little bit out. But having like 5 or 10% of the time in these episodic accretion will be consistent with this. And then evolve over here, and then you've got eventually hit the main sequence. They'll get less luminous as the pre-main sequence stars contract. Some more energy distributions, and so this is similar to that diagram I showed you before, just showing how things evolve and towards higher temperatures, bolometric temperatures, and less cell millimeter luminosity. These are the energy distributions. These are these two protostar phases as class 0, class 1. So you may be noticing here all the flux is coming out like at 100 microns in these. So why on earth would anybody want to study these things with Keck, right, which is near infrared and visible? So yeah, that's been sort of my cross to bear with TACs. But, bear with me. Talk a little bit first about where they are. So they're a lot nearby. So we all know about Orion, right? Those are the Orion clouds, like 450 parsecs away. Us in the center here. I kind of like this map of extinction with these colors being the most extinguished, hence highest density. Towards the galactic center is this way. There's this Ophiuchi clouds, Aquila, Serpens, whatnot. Turns out that there's this belt of star formation, Gould's belt. It's got a diameter of several hundred parsecs, and there are a number of star-forming regions along it. So it's a good place to study, relatively nearby, 130-ish to 400 or so parsecs. Also, it's good to study low-mass objects because they evolve slowly enough. They go through the phases before the star gets onto the main sequence. The problem with high mass gets onto the main sequence really fast, and it kind of blows up through the stages, and it's not really clear how it got there. All right, so Spitzer plus some millimeter telescopes on the ground were responsible for a lot of these catalogs, and now there's substantial numbers. These are mostly the Gould's belt regions. So these are the different stages here. So you see there aren't that many class 0 and 1s. These are like the real bona fide protostars. That's their totals. And flat is kind of like maybe like the next stage. Some of these could be 1s based on geometry. 2s are like these T Tauri stars. So if you just do a numbers analysis, you can get some idea of the lifetime of the phases. We know that T Tauri stars have a mean half-life of about 2 million years. So half-life is this interesting concept in this paper where they're looking at the mean time something moves through a phase. And they did this nice modeling of showing how the objects evolve. So this evolves to this, which evolves to that, which evolves to that. And if you go through the numbers, they get about 50,000 years in this first phase. That's where all the accretion happens, all the mass builds up. And then this other phase where the accretion really slows down and there's like dispersal of envelopes, but still a lot of circumstellar material. And then that's the T Tauri star lifetime. So things happen really fast. It is really fast, because like think about it. So I'm just thinking about this now. So what we've been a species for less, or at least a family. We've been in a family of related species that broke off from apes for like 3 million years, right? So this is like a small fraction of that time. A lot of questions about how these about the central stars here. So. What rate do they actually accrete matter? Like I showed you that it looks like they don't fit the models that well. By what mechanism? Just how does the mass actually get on the star? It's a tremendous angular momentum problem. They start off like a tenth of the mass is like a tenth of an AU away, hundreds of parsecs, and then it has to like come in, but it's also the rotational energy causes it to speed up. How do you get it to actually hit the object? So Other questions are, what are the initial stellar pre-main sequence properties of these objects? We want to calibrate the pre-main sequence models. Can you actually measure effective temperatures, stellar luminosity log G? And what about the circumstellar material? What about these jets that are driving things out, and the inner circumstellar disk? Is there, how can we see if there's accretion happening from the disks? How does the angular momentum evolve? So, how are we going to address these issues? Fortunately, we have a great tool located in a great place, right? Keck. Both telescopes have some great capabilities, and I was really struck by what Rich said, is that we have to keep our feet on the ground and remember that Mauna Kea is a really big part of this equation. Would we want these telescopes on Mount Hamilton? It would be pretty limited, right? You know, would we want them in space? Well, yeah, maybe, but it gets harder to change instruments, right? And there's no rocket that can launch them. So Mauna Kea is really the place to have a tremendous capability like this. So I am thankful for that, and I know we all are too. Okay, so getting back to the question, why would you want to look at wavelengths in which these things are purportedly invisible? Because that's where all the tracers are that are of interest to those questions. So this is a schematic from, Lee Hartman did this nice article, Annual Reviews on Accretion, of and slightly more evolved stars, how mass flows onto the star. So the idea is that there are these, what you don't see here, there's this big extended envelope out of which the thing formed. This is when it was really young as a protostar. The mass falls onto the disk. The disk just sets itself up based on conservation of angular momentum, and the disk is truncated by bipolar fields from the star, along which gas can accrete. So, mostly hydrogen accretes this way, forms an accretion shock. That causes emission lines. We can see these emission lines in spectra. Also, there are winds that come up off the disk, so there are these jets. We can see those in emission lines in spectra. We can see the continuum of the disk to measure how much hot material there is. We can see the molecular emission in the disk. We can see the densities of gas there. And and also as the gas falls onto the star, we can see, like, if it's moving away from us, because that's the part we can see, it should look like a redshifted absorption line. So there are all these probes to get at these questions pretty much are best explored in the near infrared. Optical works too, but the problem is that there's like 50 magnitudes of visual extinction still from the envelopes around here, and but going out to like K-band's a decent compromise, because then there's 10 times less extinction in magnitudes. There has been work on studying protostars on Keck. This is a little biased compilation of a few studies that I was putting together. So this is really looking at those early stages, the class 0 and class 1. So the talk is called Almost 30 Years. So I tried to actually observe one of these class 0 protostars in 1996. I was at the IFA then. Randy was my support astronomer, trying to use the LWS instrument. You may have tripped over it when you're at Keck, because it's an artifact in the lobby. But actually didn't get any data. It took a while to figure out if the instrument was working, which it turns out the answer was yes, it was, but the object had already set by then. So anyway, but I came back and worked with various people studying these class 1 protostars, studying their stellar properties. Greg here led some studies. Russell White worked with Lynn, did some. Angular momenta, these H2 emissions, sort of like, can you observe these very embedded young ones, and now doing a statistical study of these. So they've also been observed with other telescopes as well. Keck does not have a monopoly on the class 1s, but maybe it does on the class 0s at this point. People have also used these protostars as light sources to study the clouds. And lots of people have studied the slightly more evolved stars. So let's go to these class 1 things. What can we learn about them? So you may recognize this guy. Greg Dotman did this study of looking at NIRSPEC spectra of resolution of like 18,000 of protostars here in, did about 50 protostars, these class 1s. They have a lot of the same spectral features as the standard stars. And the features are a little weaker because there's continuum veiling for the hot material around there. There's some emission. This is this CO band in emission, but it's infrequent. And but otherwise was able to get spectral types and gravity information from the near-spec spectra. These mostly had absorption spectra. And also, I'll save the next punch for another one. This is sort of showing where their surface gravities are. So these are dwarf stars here. This is just this diagram of two near-infrared line indices. This is in the K-band, looking at the molecular equivalent wisps here versus these atomic ones. Low gravity objects, including giant stars and these F-Uranus things that are disk-dominated, are out here. The class 1 protostars are these red objects here, and then the dwarf stars are here. So they have like this gravity that's intermediate. It's what you would predict for pre-main sequence stars, so it's starting to calibrate the initial stellar status of these objects. This is a study done by Mike Connolly, a few other, this is actually IRTF data, but Mike is now a supported astronomer at the IRTF. Then angular momenta. So this was an interesting study. So using the NERSPEC data, Kevin Covey led this study, found that the protostars had much higher V sin I velocity distributions than the more evolved stars. And it was about less than a 0.1% chance of them being drawn from the same distribution. So it looked like they were rotating substantially faster. So which kind of what you'd expect, because stars lose angular momentum over time. But you know, what else can we learn from that? So these, I showed you earlier a cartoon, not unlike this one, where there is a poloidal field from the star going through the disk. And the idea is so that this is, the inner part of the disk is gone where the disk would be rotating faster than the star, and where that is depends on the accretion rate, but with this equation. But the bottom line is that if these protostars are rotating twice as fast as the T-Tauri stars, then they've got about 5 times the accretion rate with the same fields. And we're starting to measure the fields of the different stars, and it looks pretty similar. So that's also another smoking gun of showing that, of getting accretion rates of different objects from spectra. Looking at the H2 lines has been another productive avenue. There could be different things causing their excitation. There are a number of ones in the 2-micron band, and you look at a ratio of a couple of these lines, it changes a lot based on excitation. It goes from like 2 to 20 based on whether it's a UV excitation, which you know, young stars should have, shock excitation, X-rays. So you know, what is it? So all of these are quite possible. There should be accretion shocks giving off UV. This is mechanical shocks, so like jets coming out of it and hitting material in the cloud. X-rays, protostars have been found to be prodigious X-ray producers. So what's it going to be? This could be a good way to diagnose their environments. If you do a histogram of that ratio, it looks like it's like winds and maybe X-rays, but it doesn't look like UV is causing this excitation there. So, and you also frequently see this emission being spatially extended, so that sort of supports the wind interpretation of this. And the wind isn't. The wind could be broader than this too, because it really depends on, it's not a particularly unique ratio. So, can you go younger and understand what's happening sort of in the main accretion phase? So, I always thought it was impossible, you know, because we were told initially these things were like 30-degree Kelvin black bodies. This is like the anatomy of one of these protostars. They have strong millimeter gas outflows. They were pretty much discovered by them, and they had very cold far infrared things. However, they do have these outflows, and what those outflows do is they punch holes in the envelopes, and some light can scatter out. So this first became apparent in the Spitzer studies. This is around 2009. Studied a lot of these things. So you see, so this is K-band here, And these class zeros are over an order of magnitude fainter than these class ones, but there is still some flux. And so I thought it'd be worth trying to see if we could observe them. So again, getting the K spectra could be pretty useful for getting the stellar properties, look at the accretion diagnostics from hydrogen lines and molecular emissions, use the calibrations that have been established with the more evolved stars. So object selection is pretty tricky on these because you want to make, a lot of stars we know are binary, and you want to make sure the same thing you're looking at in the near infrared is the thing that's really the class 0, and also want to make sure that it's visible, but it is possible. And so now, thanks, did a little initial explorations, but also been collaborating with Lynn in a project led by Lynn Hillenbrand, led by in a project that the analysis is being led by Valentin Lugulek, who's a postdoc working with me. So we've got about spectra of 26 of these things now, these class zeros, and in the Gould's belt. And they're pretty different. So only about 25% have these absorption lines where you could see the pre-main sequence star versus something like 80% in the class ones. There are many of these. You see this big feature there? So there's these big emission features in this carbon monoxide. About half of them have this. This is very different from the class ones, where only about 10 or 15% have these. That's indicative of very dense gas, like 10 to the 9th particles per cubic centimeter at temperatures of about 3,000 or 4,000 Kelvin. Stronger other emission lines of these hydrogen and the H2 emission lines than class ones. This is sort of taking apart one of those spectra of one of these objects. Beautiful Mossfire spectra. I should say that just about all but one of these spectra are Mossfire. I think one of these is NIRSpec here, but Mossfire has been great. This is looking at spectral resolution isn't great, but it's good enough to resolve the lines. So this is like this bracket gamma line, this hydrogen line. It doesn't have the classic line profile that we would often see in older stars for accretion that is consistent with that material falling from a disk. It could be another style of accretion going on that's more appropriate for this higher rate that these things are undergoing. This also has these strong carbon monoxide band heads and bands, and but dominated by this whopping H2 lines, right? Like these strongest lines are H2. So Valentin put together a table of all these 26 objects. What do they show? But if you just look at the comparison between these really embedded objects, these class zeros versus the class ones, the much higher fraction have these H2 lines in the class zeros, much higher fraction have this CO, and than the class one. So there's definitely different processes going on. These are just some of the comparisons. These are these cumulative distribution functions. This is this carbon monoxide emission. So like half of them of the class zeros have this, and it's much brighter too relative to the brightness of the star and equivalent width than the class ones. Red is class 0, blue is class 1. Also for the bracket gamma line, not quite as common, but stronger. Here is equivalent width for the hydrogen line. So the hydrogen lines are stronger and they have stronger luminosity. These are also the distributions for the two different functions, for the two different classes. And the ratios, though, of the H2 lines are pretty similar. So they both, the histograms overlie each other. So it's both actually quite consistent when you deal with the extinction properly with mechanical shock excitation. So it's looking like the hydrogen jets are indeed kind of coming out from these stars and are likely driving the outflows, the really massive cold outflows that are seen in the millimeter. So that's what I have, and I just want to leave this summary here saying that Keck data really have revealed the initial stellar properties of protostars. These protostars, both the class 0s and 1s, have strong spatially extended hydrogen lines that are consistent with jets. The youngest ones have a lot of other features that hint at stronger accretion and are indicative of stronger accretion. We're trying to model that in more details, although we haven't really pinned down the specific mass accretion mechanism for these youngest objects. And these are just a picture of some of the people that have contributed to these Keck studies. So thank you.